So in this video, I wanted to talk about the heat effects in a CSTR. So really fast, I'm just going to show you how you would apply the general energy balance to a CSTR at steady state, and then quickly show you how to size a CSTR based on the information you have. So first of all, I'm just going to write heat effects in a CSTR. So first of all, we want to start with the general energy balance equation. So that was Q minus shaft work minus FA naught sum theta I CPI T minus TI naught minus the heat of reaction at the reference temperature plus delta C sub P T minus TR multiplied by FA naught X is equal to 0. And I think that got cut off, but so for a CSTR, first of all, we want to replace FA naught X by RAV. So FA naught X is equal to the rate multiplied by the volume. And that comes from the CSTR mole balance. And also for large values, large rates of coolant flow, we're going to say that Q is equal to UA TA minus T. And remember, this is for large coolant. So basically the temperature of the fluid entering your heating or cooling jacket is approximately equal to the temperature of the fluid leaving. We're going to assume that work is 0 and that delta C sub P is 0. So if you do that, you get, so setting work to 0, setting Q to this, and plugging this in for FA naught X, you get the UA over FA naught multiplied by TA minus T. And I also divided everything by FA naught plus the sum of theta I CPI T minus T naught multiplied by delta heat of reaction X is equal to 0. So then what we want to do is solve this equation for X. So X is equal to UA over FA naught T minus TA plus the sum of theta I CPI T minus T naught, and this is over negative heat of reaction at this reference temperature. So then this equation can be coupled with the CSTR mole balance, which is V is equal to FA naught X over the rate, which is a function of X and T. So you can use that, you can use this mole balance and then the energy balance to size a CSTR. So now I'm just going to erase this step real quick, and I'm going to show you the algorithm for sizing a CSTR depending on what information you have. Coming over here, I'm just going to say algorithm for sizing a CSTR. So let's say that you have A to B, assume it's liquid, and you know FA naught, CA naught, your rate constant, you know E, you know CPA, you know the heat of reaction at some reference temperature. You know that delta C sub P is 0 and theta B is 0. So the first thing you want to do is a mole balance. And so for a CSTR, that's just V is equal to FA naught X over minus RA. You write your rate laws, and in this case, this is assuming elementary rate law. This is K CA, and then K is equal to K1 exponent E over R 1 over T1 minus 1 over T. And this is all assuming that you know A. This is also equal to A minus E over RT. And for the stoichiometry, this is liquid phase, so we know that Ca is equal to Ca naught 1 minus X. So then we can combine everything. And if you do that, you get the V is equal to FA naught X over K, Ca naught 1 minus X. And just remember that you're plugging in this for K. From here, there are 3 different routes you can take. First of all, if you know what your conversion is, so know X, then you find V, you find your volume and your temperature. So you would do that. First you would calculate T from an energy balance, and that's the one we just looked at. So that was T is equal to FA naught X minus the heat of reaction plus UA TA plus FA naught CPA T naught over U A plus FA naught CPA. And just remember, this equation is assuming delta C sub P is 0, and also theta B is 0 in this case. And so you would calculate the temperature, and then you would use the temperature to calculate K. So KT is equal to K1 exponent E over R 1 over T1 minus 1 over T. And then you would calculate the volume. So V is equal to FA naught X over K CA naught 1 minus X. Now at this point you should know everything, because for temperature you know FA naught, you know X, you know the heat of reaction, you know, I'm going to say that UA is also known. You should know the ambient temperature, FA naught, CPA, T naught. So, and then for K, you know E, and then for V, you know K because you just calculated it, and you know X, FA naught, and CA naught. So then this is number 1. So for number 2, you know the temperature, and you're going to find the conversion and the volume. So for that, and I'm going to erase this real quick. I was hoping this would all fit side by side, but I don't think it will. So for this one, first you calculate x. So x is equal to u a over f a naught t minus ta plus the sum of theta I cpi t minus t naught. And that's multiplied. So this is all divided by the heat of reaction as some reference temperature. So from that, well, we already know the temperature, so we can calculate K, and then you calculate V. So I'm going to erase this real quick and then show you the. Actually, I'm going to erase stuff over here. So for the third option, you know the volume, and you're going to calculate the conversion and the temperature. So for this, you would use you would calculate x from your mole balance, and so in this case that's tau k over 1 plus tau k, where tau is equal to v over v naught. And then we can plug in an equation for k, so this can be rewritten as x mole balance is equal to tau a e to the minus e over RT over 1 plus tau a e minus e over RT. And you can calculate x from your energy balance, and that is u a t minus ta, this is over f a naught, plus cpa t minus t naught over the heat of reaction. So then what you would do is plot x and t. So this is x, t. So you plot your mole balance, and I don't know, let's just say it looks something like this. So x mole balance, and you plot your energy balance. So let's say that looks like this. And this, where they meet, is your conversion, and then this is your temperature. So in the next video, I'm going to talk about steady states in CSTRs, because as you'll come to find out, CSTRs can have more than one steady state.